All right, this is day 5, part 2. So if you remember from uh, the last one, we put everything in order, correct? Made sure the page numbers came, X came before Y, and we got the middle page number from the correctly ordered updates, right? So now we're taking it one step farther. For each of the incorrectly ordered updates, we use the page ordering rules to put the page numbers in the right order. So for the above example, here are the 3 incorrectly ordered page updates and their correct orderings, which you see there. After taking only the incorrectly ordered updates and ordering them correctly, their middle page numbers are 47, 29, and 47. Adding these together produces 123. So we need to find the updates which are not in the correct order. And what do you get if you add up the middle page numbers after correctly ordering just those numbers? Okay. So, like I said, last time we wrote the program that checked if the list of pages followed a specific set of ordering rules. Like page 47 must come before page 43, or page 15 must come before page 20. And then we found the ordered updates and calculated the sum of all their middle pages, and that's where we came up with whatever the number you had last week. Mine was 7365. So now we're going to deal with what's known as reconstructing. So we're going to be reconstructing the correct sequence based on these new set of rules. Now there's a algorithm that's specifically made for this kind of problem inside of JavaScript. So where we have a set of items and a series of must come before dependencies, and the algorithm's known as a topological sort. And I'll get into that here in a minute. So here's what we have to do. We need to take the incorrectly ordered updates from part 1 and rearrange them into a valid sequence according to the rules. And we can't just use simple sorting, and we'll get into why we can't use that here in a minute. We're going to use the concept of representing our rules as a dependency graph. And so the topological sort. So let me think about how I'm going to explain that. It gets a little confusing. We are going to have to build a separate dedicated function to perform the sort, and then modify the script from part 1 to identify with the incorrect updates, apply the sort to it, find the middle element of the corrected sequence, and calculate the final sum of all those middle numbers. All right. So what would be the first part? Let's get into it. Let's go to here at the top. So the first thing we need to do, we leave this, the is update valid, because that still applies. You know, we're checking the provided update sequence against every single rule. And then we have our for of loop, which is providing a clean and readable way to iterate over the elements of every iterable object, such as our rules array. And then in each iteration, rule will hold one element from the rules array. Now, then we immediately use the array destructuring assignment, which is X must come before Y. And that's none of that is changing. So what we're going to put in here after that, we're going to add another function, and this is going to be the topological sort, and we'll put Pages. Or rules. Okay. So what this does, a topological sort finds a linear ordering of nodes in a directed graph, such that for every directed edge from node U to node V, node U comes before node V in the ordering. And I'm pretty sure I probably confused you. So let me break that down. So when you have a set of items and rules stating A must come before B, or in this case, X must come before Y, and then C must come before D. That's a scenario that can be visualized as like a directed eclectic graph where nodes or vertices, each page number in our update is a node on the graph. And then you have edges or arcs. So each X must come before Y, or each X and Y represents a directed edge pointing from node X to node Y. And that signifies that X is a prerequisite for Y, or A is a prerequisite for B, or C is a prerequisite for D. Um, so that's when you have the topological sort. And like I said before, that's a way to find a linear ordering of those nodes so that for every directed edge from node X to node Y, X must come before Y in the ordering. Now, to confuse you even more, this is only possible if the graph has no cycles. And a cycle would be like A must come before A, or B must come before B, or C must come before C. In this situation, that's impossible. So you need to build the function robust enough to prevent that. Now, this puzzle should not have any cycles because we're going to build it out robustly enough to detect them and prevent them. Now, how do you find like linear ordering? So a common method is what's known as Kahn's algorithm. So it works like um, imagine you have like a list of college courses and their prerequisites are calculus one must come or must be taken before calculus two. How do you figure out a valid order to take the courses? First you have to find a starting point. So you have to identify all the courses that have no prerequisites, as in like, hey, you don't have to take that class before you can take this class. You can take these first. In our graph or our input doc or our graph that we're creating, sorry, these are nodes within in degree of zero or no arrows pointing into them. Nothing saying X must come before X or Y must come before Y. Then you have to process and remove. So you have to pick one of those starting courses and then you add it to your schedule, or in this case, it's our sorted list. And now, like you imagine you completed it. So you need to tell all the courses that depended on it that you fulfilled their prerequisites. In our graph, we're going to remove the node and its outgoing edges. And then from there, you have to update the dependencies. So for each course that depended on the one you just finished, you decrease its count of remaining prerequisites. So in our graph that we'll make, we decrease the in degree of the neighboring nodes. So then after that, you have to find a new starting point. So after you remove those prerequisites, any of the dependent courses now have no remaining prerequisites. They become the new starting point. So you add them to your list of available courses to take next. And then you just go through that cycle over and over and over again. You just keep picking available starting points and add it to your schedule, or in this case, middle numbers, and add it to our count and updating the count as you go along until you've completed all the math on it. Um, think right now that's like the best way I can think to explain it. And I'll see if I can come up with something a little more thorough and put it in the description of this video and email it to y'all. But that took me a little bit. That took me a little bit to break down today for you. So on this, the pages to sort, that's the specific array of unique page numbers that are present in the update that's currently being reordered. So like the number like pages 61 or 13 and 29. Um, relevant rules, which is the next one. That would be an array containing only the rules X, Y, where both X and Y are present in the pages to sort array. That focuses the sort only on the dependencies within the current subset of pages, like 23 and 13, and then 61 and 29. So from there, we need to do the cons algorithm. We need to efficiently represent the dependencies of the rules as a directed graph. So we'll use two core data structures implemented with maps for potentially better performance with non-integer keys and clear intent. So we would do in degree equals map. So in degree, it's a map where keys are page numbers and values are the count of incoming edges. So this is going to track how many prerequisites each page has within the specific set of pages and rules. So for example, if rules are A must come before C and B must come before C, then in degree would be C equals 2. And from there, we're going to do equals again, new map. So this is adjacency list, which is a map where keys are page numbers and values are arrays of pages that directly depend on the key page. So like example, the pages that the key page points to. So example, if the rules are A must come before B and A must come before C, then that would mean uh, the adjacency list is A and B and C. It would be A equals, you don't have to write this out. This is just for example. I don't know what bar prop, why that showed up. It would be that. That's what that would convert to in that scenario. So now we put our for loop in this. So before processing uh, the rules, we need to initialize entries in our maps for every page. That is part of the specific sorting task, which is the pages to sort. Now that makes sure that even pages with no rules attached are included in the process. So that's supposed to capitalize. So page of pages to sort. What the heck? It's shifting, it's going down. There you go. And then in degree, set page. Here, now what this is. So that is setting the initial in degree count for each page to 0, and we'll increment this as we process rules. Next thing we need to do is set the initial list of dependents or the outgoing edges for each page to an empty array. And that would be set page, and you put it into an empty array. Now, after this, we go to step 2. We need to iterate through only the rules that apply specifically to the pages inside of pages to sort. So each rule, which is X and Y, represents a directed edge of X must come before Y. So we would for X, Y, relevant rules. Now from there, we need to put a safety check in there like we did for part 1 of day 5. Well, what we need to do, we need to ensure both pages in the rule actually exist as keys in our map. And then to prevent any errors if the filter and logic fails or has a flaw. So that would be X in 3 has Y. And from there, we add the dependency, which is like page Y depends on page X. We retrieve the current array of dependents for page X using get, and we'll add Y to this list using probably push. So get X push Y. And now we need to increment the in degree count for page Y, signifying that it has more prerequisites of X. And then we retrieve the current count. Again, we'll use get, and we'll add 1 and update the map using set. So we'll do in degree set Y in degree dot get and we add 1. Okay. Now we go to step 3. And I swear after step 3 it gets a little easier. Now we need to initialize the queue or the starting point. So we start by finding all the nodes or pages that have an in degree of 0. Now these are the pages that have no prerequisites within the set. So they can appear first. And we just use a simple array queue to hold the starting nodes. So we'll do let's do that. What do you do for that? And we'll do yeah. Page of pages to sort. And we're going to check the in degree count we calculated for this page in the previous step. So if in degree get page equals 0. Now, if the in degree is 0, we add this page to our processing queue. So we would push it. Yeah. Push the page. Whoa, what is Okay. Now, this part is like critical for determinism. So if the graph structure allows for multiple valid topological sorts, like for example, if both A and B have no prerequisites and the rule exists between them, or no rule exists between them, the order might depend on the arbitrary order they were added to the queue. So to ensure consistent, predictable output, like especially important for like matching examples or specific requirements, we sort the initial queue numerically in ascendant order. So we would sort A, B. So the sort callback A, B, and then A minus B, that's the standard JavaScript idiom for numerical or sorting. Now, I believe this will be the last um, step. So, which would be step 4. We need to process the queue. So this will store our final topologically sorted sequence of pages, which would be the result. Put in an empty array, and then the main loop continues as long as there are pages in the queue waiting to be processed. So if the queue becomes empty, the algorithm terminates, and we show that doing this. Well, queue length 0. We would use equals queue shift. So what this is saying, the main loop is continuing as long as there's pages waiting to be processed. If the queue becomes empty, the algorithm terminates. Then we need to dequeue it. So, which is that. We remove the first element from the front of the page, which is then the shift method modifies the queue array by removing the first element and then returns that element. That follows like FIFO, first in, first out behavior, which is expected of a queue. And I use Q to represent the current page that's being processed. Oh, missing something. Oh, we need to add it. We need to add the page to the end of our final list. So we would result push you. We're adding it to the end of our final list. Now we need to simulate removing you, like node, like you, and its outgoing edges from the graph. Now we do this by considering all nodes V that had U as a prerequisite. So we're going to retrieve the array of pages that depend on U from the adjacency list. So we'll call them neighbors. And we're from the adjacency list. And there we go. And there's a chance that that'll be an empty array, and that's okay. Now from there, we need to sort them numerically. Kind of like sorting the initial sequence, we're going to make sure that if processing U makes multiple neighbors ready simultaneously, like their in degree becomes 0 at the same time, they will be added to the queue in a consistent, predictable order based on their page number. So we have to sort them. Sort. Again, it's just like the last one. And A non-SB. And from here, we are going to iterate through each of used neighbors. Yeah, we're going to iterate through each of the used neighbors. So that will be for const v of neighbors. We're going to decrement the n degree count for neighbor v because its prerequisites of u have now been met. So we would do const new n degree equals n degree get v minus 1. Oh. Yeah. Set. And then from here, we have to check to see if this now neighbor V has an n degree of 0. So you would, if new n degree simply 0, if it is, then we push it into our queue. Not pushy, but push. Okay. Now, after potentially adding multiple new nodes to the queue in the inner loop, we resort the entire queue numerically. Now, this makes sure that the next node we process in the next while loop iteration is always the lowest numbered available node among those with an n degree of 0. And that guarantees a single deterministic output for any given input graph. So you just sort them. Not support, but sort. A, B, same thing. A, B. No. Minus B. Okay. Now that's the end of our from here we're at the end of our while loop right there. And it'll repeat through until the queue is empty. The next thing we need to do is check for the validation of sort or cycles. So a fundamental property of topological sorting is if the original graph contains a directed cycle, as in A must come before B, B must come before C, but C must come before A, then the nodes involved in that cycle will never reach an n degree of 0 because they will always be waiting for the other. It's impossible for A to come or C to come before A since B has to come before it and A has to come before B, as an example. So consequently, they will never be added to the result list. So a successful topological sort must include exactly the same number of nodes as the input. So you make that happen. Length. Pages to sort. The length. So if the number of pages in our result array is different from the number of pages we started with, it indicates that a cycle was present in the relevant rules and a valid linear ordering is impossible. So we throw an error from there. Console error. This broke. And we'll do pages short. And from there, we return null to explicitly signal to the calling code that the sorting process failed. Now, if the result length matches the input length, then the sort was successful. We return the result array, which is going to contain the pages in a valid topological order, which is super easy. It works. And now, excuse me. From there, we go into the try catch block that we used. Was it Friday? The other day when we were doing it. Not much changes inside of here. Some stuff changes, but not much. We still keep the file content, all that. We keep sections. We keep rule sections. We keep update sections. None of that changes. We don't change if update sections, console error, none of that. What we are changing is we now have to parse all the rules instead of just the rules that we were doing on Friday. So the rules section string, we need to process the rules section string into our desired data structure, the array of number pairs that we did Friday. So we need to split the section into individual lines using the regex that you see there that handles different line endings. We use map to transform each line string. And then inside the map, we use line.split and then the or to create an array of two strings. Then we map number. So it's chained immediately to convert this array of strings into an array of numbers. And then destructuring, const x and y assigns the numbers to variables x and y, and then we return it. So the only thing that we're going to change in there is we're going to take rules and we're going to make it all rules. Okay. And we're doing the exact same thing for updates. We're taking it from updates to all updates. Now, we need to initialize the accumulator for part one sum, the middle pages of the initially valid updates, what we did on Friday. So we're just going to change that to or add part one on the end. And then we need to create a new empty array to store references to the update arrays that fail the part one validation. That we need to keep track of these specific arrays for processing in part two. So we'll call them incorrect updates. And that's not right. Yeah, incorrect updates. And we put them into an empty array, not a minus equals, into an empty array. Now, only thing we're changing inside of here is instead of just rules, passing all rules. Middle page number, const middle index. Yep, sum of middle pages. We're going to change that to part one. And we're going to change this. We're going to change this to, we're going to add the page number that we found at the middle index to part one of the sum accumulator. So we would do update. Middle index. Oh, we already have that. We're just adding the page number part one. Mm, page number- Why am I throwing errors? What am I missing? The sum of middle pages, part one. Middle index. Is up valid. Michael. Back. 4, 2. What's this say? Okay, well, that's fine. Put something else in there. We'll read it at the end. So if the update is invalid, we add a reference to this specific update array into our incorrect updates list. So we're not going to copy the array. We're just storing a pointer to it for later use in part two. So incorrect updates, push it, update. And then from there, we print the final result for part one. Okay. And we can get rid of, okay. So for part two, um, let's see. Yeah, so for part two, we initialize the accumulator for part two sum, which is the middle pages of the corrected invalid update. So that's lit. Lit. You know what? I was being dumb. That's sum of middle pages part two equal 0. Now we loop only through the updates that we previously identified as incorrect and stored in the incorrect updates. So for correct updates, uh, checking for update. Uh, incorrect updates. We need to filter it. So before sorting, we need to filter the all rules list to get only those rules that involve pages actually present in this specific incorrect update. So rules involve pages not present in this update are irrelevant for ordering it. So we create a set from the pages in the current update. And a set is a data structure that stores unique values and provides extremely fast lockups or lookups using the has method. This is like way more efficient than repeatedly using array includes or array index of inside the filter. So we pages in pages and update equals set incorrect update. So now we use the filter method on our global all rules array, and that's going to create a new array. So the filter's callback function will be X, Y, and so just um, I don't know, applicable rules equals all rules filtering X, Y, and then pages and update and X and pages and update must have Y. Okay, so the filter's callback function here receives each rule pair, and it keeps the rule only if the pages and update set contains page X and also contains page Y. Now, from there, we call our topological sort function, passing the specific incorrect updates array and the filtered list of applicable rules. And this will attempt to find the correct linear order. So we'll do oh, an update equals sort and incorrect update and applicable rules. So if the topological sort function returned a valid array, like it didn't return null, that's what we need to check for, because a null return value indicates that a cycle was detected and sorting was impossible. So if sorted update, so if the sorting was successful and we received the sorted update array, we're going to now calculate the middle index of this newly sorted array. So middle index, I'm going to get rid of my errors now. Equals get sorted update. Length 2, so that'll give us a middle index. And then we got to get the middle page number at the middle index from the corrected sequence. Equals sorted update. Can't believe I missed that. And then after this, we just need to add the middle number to the part two accumulator. So sum middle pages part two. We added two middle page number. I think I need to put that same exact logic up there. I think I'm missing that. Wait a minute. Oh, no, I'm gonna leave it off. I might not. I'm gonna leave that. Ignore me. Okay, from here. So if sorted update is null, it signifies a problem, which would be likely a cycle in the input rules pertaining to the update, which shouldn't happen based on puzzle constraints, but it's good to handle anyway. So we'd log a warning message indicating, which update failed. We do not want to add anything to the sum for this failed update, but we'll do a console warn. Console warn. Couldn't update. Update. Resume. Okay. Oh, now we console log. Favorite part. Part two. Some of middle pages. Oh, that's middle pages. Correctly updated. Is middle pages part two. Then from there we catch an error. Now let me look at this. That's not being called. Sum of middle pages part one. Oh, that's why. That's why it was weird. So this should read over this. So when we run this, it should show both numbers. Should for me, it should show the 77365 for you, whatever it is, as well as the second number. I started to work on this earlier and then got pulled away with work, so I didn't get to really test it out. I just were about to. Stupid. A new one. No. That's a Xiaomi. Where 82. Updates is not defined. Sure it is. Um, oh, that's right. It's all updates. You had it. Yeah. See if that did it. No, it still doesn't like me. Middle page number part 1 is not defined. Oh, middle pages. Some of see if that works. I got errors everywhere. I called it Quest. That's a one-handed typing for you. Hey, there it is. That worked. 5770. Yeah, that's right. That's good. Okay, how confused are you?
Certainly.
How confused are you, Indigo?
Oh, definitely. I'm still on the first error message that says updates is not defined.
Okay, share your screen.
Okay. All right.
It's so go up. You see line 83?
Yes.
Change it to all updates.
Oh. Okay. All right. Okay.
Okay, what we got there? Some is not defined. 87, line 87.
Oh.
Yeah, you can get rid of that. Highlight over where it says const sum of middle pages part 1. Why is that underlined? It's like it's not being read. Sum of middle pages part 1. So Let's see what you got there compared to that. Move your mouse. For this update valid, update constant middle index, sum of middle pages, part one. Okay. Where it says equal update, put plus equal.
Equal update.
Yeah, line 86.
Oh,
Yeah, and then get rid of const. Okay.
mm-hmm.
Let's see what other error we get.
Okay.
Mhm.
No. The
Q is not defined.
mm-hmm.
That's the same one I had. You probably typed what I had. I typed quest by mistake. What line 39?
Oh
Yeah,
yeah.
it's new. Yeah, I had accidentally typed quest. And now save it and run it, and it should give you a correct answer. You got. Oh, we went through this before too.
Yeah,
So
I got my console dialogue in
you,
the wrong.
you got it in the wrong place. So let's see where you got your console log. Yes, you do.
Okay. one bracket out.
So let me see where you have that one. So those two. Oh no, that one's correct.
Oh.
That one's in the correct spot. The one above it's in the correct spot. That console log's in the correct spot. Huh. That's the only console logs that we have in there.
Oh.
Okay. Let's
Couldn't update. Couldn't update.
Okay, something's wrong here. So let's go through yours. Let's start at the top.
Oh, at the top of the okay.
Yeah, I'm gonna stop sharing so it makes your screen.
It's like a red dot right here. What is it?
That's the line that you're on.
Oh.
Okay. All right, and now yours is bigger. Okay. Next is all right. Scroll down. A little up. Logical start, pages to sort, relevant rules, and degree new map. There's new map, page of pages to sort, and degrees. Set page for context Y of relevant rules. Has X and in degree has Y. Get X push Y. Degree set Y and degree get Y plus 1. All right. Q, const Q equals const page of the sort. In degree get page equals 0. All right. Hey, you see where it says Q micro test?
Oh.
Let's change that to just Q. Q dot push, and let's scroll down a little more. Q sort minus B results empty array while Q length greater than 0. That's Q shift. Okay, go down a little bit. Q sort Console error. Blank. Let's go. No. Turn result. All right, go down. All right. I mean, all that should be right. Run it again.
Mm. Oh my gosh.
Doing that crap again. All right. Let's work from the bottom up. Okay. Console error. Yeah. Two. That's the one. Some of middle pages, part two. Page number. I mean, it's telling me, by the way it's doing that, it's telling me that the console log's out of whack, but that's not it. On. All right, go up. Okay. Into. um, Okay. What is? You see that other console log you have in there?
Right here.
Yeah, no, never mind. That's right. Take it back. Some middle thing. Yes, updates. Okay, go up. Okay. You didn't change any of that, right?
No,
All right, go up.
it doesn't matter that I have this folder open too.
No.
Oh.
Uh-huh. Go up. Okay. All that looks all right. Go up. I see nothing wrong with this. Go up. Hey, copy all that code and put it in the chat. I want to put it in my terminal and see if it works, if it does that.
Okay.
See if we can see what's missing. All right. What the- Oh, some words got copied in that one. Why it threw that error. Yeah, it's doing it. Okay, it's doing the same thing. So there's some kind of error somewhere. Let me split this. and compare it. Okay, let's do this. Okay, and we'll split that, right? All right, let's see if we can find what's funky here. Mhm. I cannot see any difference at all.
Hmm.
But there's obviously something wrong because it did it in mine too. Uh, what if I put save that node? Yes, Dr. Did the same stuff. See if there's a typo somewhere. There's obviously a typo somewhere or something.
Right.
63. Michael, did yours work?
No,
You doing the same thing?
not really. It's just looking at says unexpected end of input.
That's a new one. Okay. I wonder if you just have like oh. I bet you that's it. Let's see. I think I found your problem. There you go. I just put it in the chat for you. Go ahead and put that in there. They're still doing it? Oh no, no, it is 4679. Do you want to know what it was?
What was it?
So your console log,
Mm,
your last console log, you had a space after log before the parenthesis.
that's why.
Yeah, if you look at what you sent to me. Yeah, it caused it to do that. All I did was I took the space out there and it started working.
Talking about like right here.
I can't see.
Oh,
Where?
right here
Yeah, but there was a space on yours.
in the terminal or over here. Okay.
Mhm.
Okay.
So let's see if that number's right. That's the right answer, yay.
All right.
Michael, you want to share your screen? I think you're muted.
Oh yeah, I see. Okay, but I was trying to figure out myself. I see it. It's a error for the brace, curly brace. I'm missing a closing curly brace.
Oh, okay. Let me
But
sure you get the right number. So I am sending you guys right now as we're on here. I am sending y'all what was put together for this. Let's see. Compose. All right. There we go. Michael. Okay, 5. There you go. I just sent you what I had for this. Or it'll explain it way more.